and change over the presentation to you. And here comes
All
the
right,
presentation. So,
from the screen.
and I see your screen. I see your
You,
elephant. So
the
let's.
elephant. All right, that's my elephant. All right, let's start this. All right, you seeing
And I've
it?
got it. Yep, I do.
All right, great. Well, welcome everyone. Appreciate you joining. I hear it was pretty short notice too, so again, I blame myself for that. I've had Tom scrambling a while, changing dates and everything. So, but I appreciate everybody showing up at short notice to talk about what's new in virtualizing Hadoop. Um, and to echo Tom's note previously, I can't remember, but I don't know if I said it as strong, like never say never. I was a SQL DBA for quite a few years, and I remember one of the last places I worked before Hortonworks, early in 2000, mid 2000, 2005 maybe. There was a mandate to virtualize all the Windows servers. So that included every SQL server. And at the time, we kind of balked and we said, no, there's no way you'll ever be able to virtualize a database, a SQL server. And they were like, well, we're going to do it anyway. And so we expected the entire world to collapse. And at the end of the day, the SQL servers actually ran faster because it was on newer hardware. So I've learned from my past experience that never say never about any possible technical solution. But I think the theme here is that virtualizing Hadoop, though possible, needs a certain level of understanding and implementation in order to do it right and get it working correctly. So quick introduction. This is me. I'm Scott Shaw. I'm a Senior Solutions Engineer for Hortonworks. I've been with Hortonworks for about 2 years. I have about 15 plus years in data management, ETL design, SQL Server architecture, data architecture, and then I've been actually working with Hadoop for about 3 years. You can reach me at shaw@hortonworks.com or just follow me on Shaw SQL. I tweet every now and then. I'm not very prolific, but a quick disclaimer. We can read this when I hand out the slides, post the slides to Tom. But just know that there may be some future mentions here that are not guaranteed, and that there is no contractual agreement. So that's done. We can thank the lawyers for that. All right. So, like I said, when you talk about virtualizing any platform, especially a complex platform like Hadoop or even a database platform like SQL Server, I think it helps to understand how it works, right? So for example, if on another technology, if you're looking at antivirus, you would run antivirus much differently on a file system than you would on, let's say a MDF file for a SQL Server, right? You just wouldn't do it. So there's some caveats with virtualizing Hadoop, but before you can understand those caveats, you have to understand the basics of Hadoop and what makes the Hadoop data processing different than your standard file system or standard processing. So let's first start off that, and hopefully this isn't too much in review for everybody. But let's look at Hadoop. Hadoop is actually two things. Hadoop is storage, HDFS, Hadoop file system, and compute, as well as a resource management framework that helps divvy out resources. So again, we'll look at this. If you look at a virtualization, you have your ESXi framework that is responsible for talking to the server kernels and divvying out memory resources like memory, CPU, and things of that nature, I/O. Something to keep in mind is that Hadoop has that built in already in Yarn, so there's some overlap in how resources are managed. And as we'll see later, there's actually a concept of a container. So So there's two parts, the HDFS and the compute. And the compute tends to be any kind of data engine, whether it's Spark, TES, MapReduce, something of that nature. It's a compute framework that understands a distributed file system. So when we say a distributed file system, it's essentially a file system that runs on top of potentially thousands of servers, but looks like a single directory. So the fact that the file system is distributed is actually obfuscated from the end user. And as we'll look deeper, if that distributed file system is not transparent to the virtual environment, it can also cause problems. So the whole purpose of Hadoop processing is this divide and conquer mentality. So Hadoop was initially designed, and still is designed, to take a very large problem and break it up into small pieces and then execute against those pieces in parallel against a distributed system, and at the end of the processing bring it all back together and bring back a result. So that is the core tenet of Hadoop processing, and really the only method to tackle really large problems that we call big data problems. So it does that by splitting up either tasks or the data itself and storing them on various nodes within the cluster. The benefit of that in a Hadoop environment is that the larger your cluster is, technically the more scalable it is and the faster it's going to compute, because you're going to increase that divide and conquer paradigm. Another thing to think about is that HDFS is a write once, read many, or worm architecture. It means that it is a file system that is immutable. Once a data is written, it is never overwritten. It can be appended to, but it can never be overwritten. Some other points is that HDFS is a logical file system that sits on top of a native OS. So you would install your Linux system and then install HDFS on top of it. As we'll see in the next few slides, files are split into what are called blocks. Again, it's this divide and conquer process, and then blocks are spread across the cluster. So let's take let's take an example here. So you have a 400 megabyte file. That file, the default block size for HDFS is around 128 megs. That's adjustable anywhere between 256 and 64 megs. Normally, by default, it's 128 megs. So it'll split that block up into equal 128 megs. So each block is the same except for the last block being written, which maybe is most likely going to be less than the default block size. Now, what's critical to understand is that not only is it splitting those blocks up, but there is an algorithm to how it writes those blocks to the nodes, to the data nodes in your cluster. And a data node is essentially the storage portion of your cluster. It's where the actual work's going to be done, where the data is stored and the work's going to be done. So there's actually a algorithm, built-in algorithm to the software that tells the process where to write those blocks. And in a bare metal architecture, and let's say a bare metal multi-rack architecture, what's going to happen is that the first block is going to be written to a node on the same rack as the process, and then the second block will be written off rack, and then the third block will be written also off rack but the same rack as the second block. So with a block replication of 3, you get a built-in redundancy to your file. So each file is going to be split into blocks, Each block is going to be replicated 3 times, and each block will be not only written to a node on a rack, but also written to a node on another rack. So essentially, HDFS out of the box is a rack-aware application. And keep in mind that this replication and this redundancy is built into the software. So so redundancy within HDFS is not hardware controlled. So this goes back to the tenet of HDFS that allows for low-cost commodity hardware that expects failure because the redundancy is software-based and not hardware-based. So we have built-in redundancy. We have rack awareness. The other thing we have then is the processing of the data. So that's the storage of the data, how data is written for HDFS. When you look at Yarn, Yarn is responsible for managing and monitoring jobs within a cluster and resource allocation. So there's this concept of an application in Yarn, and an application is simply a temporal job or service submitted to the cluster via Yarn. So this can be an H-based job or a MapReduce job. It could be like a TES job, like doing a select star from a file. And then what will happen is once that application is submitted or that task is submitted to the cluster, there is a node manager process on each individual node that will spin up and allocate what's called a container. Now this is a little different than a Docker container. What this is a JVM container that contains your resources, your memory and your CPU, and in the future it will contain things like I/O and network resources too. So it literally is just the smallest unit of resource allocation. And so things have to, there's kind of this resource dance that occurs where the job is submitted, the resources are allocated, the job processes, and at some point the job ends, and there's a notification back to the resource manager that says the job is done. You can either start up another job, or you've completed all the tasks in the job, and now you're ready to move on. Now the thing to keep in mind is that this is node-based processing. So this same pattern can occur on multiple nodes in your cluster in parallel. So it's not just you submit a single job, it allocates resources, does compute, and at the end you get your answer. This is actually a scheduling and monitoring dance that occurs throughout your cluster and could possibly be running on thousands of nodes. So it has to take into account failures. One is if a task fails, how does that task get resubmitted? Who's responsible for resubmitting it? Who's responsible for knowing where the blocks are located, where the data is located on which node to be processed, and how do we know that all the data has been processed and that the answer is available? So lots of stuff going on in a distributed environment, which makes memory allocation, CPU allocation, and processing extremely complicated. So there are essentially the allocation of the resource. How many containers do I allocate? And really, containers are generally just divisible by the amount of RAM you have. So you may have 5 containers with 8 gigs of RAM, so total of 40 gigs on the node. So you're essentially just splitting up your container sizes based off the available resources you have per node. And there's ways you can create resource groups in which, if you have higher capacity servers, you can create more containers on those servers than you have in other nodes that may have less less resources. And then again, how do we make sure that when multiple jobs are submitted that they don't steal resources from other containers and other jobs, and that there's some isolation involved. And so what does all this again are these major Yarn components. You have the resource manager, which is responsible for allocating resources, accepts job submissions, and communicates with the application manager. It's the node manager that then is responsible for essentially querying the nodes and allocating the available containers. Or it might come back and say, you know what, I don't have any available containers left on this node. You're going to have to execute that job someplace else on another node, maybe a less busy node in the cluster. And then finally, the application manager, which negotiates the resources as well as monitors the task and determines whether the task has failed, whether it's still in a running state, whether it's started, whether it's completed. So that's essentially the software components of Hadoop. It's a quick overview where we look at the, essentially the compute, processing, the scheduling and the resource negotiation processing, as well as the storage. And we'll find that all three are going to be critical to implementing virtualization. So let's look at real quick at a cluster architecture. Again, hopefully this isn't too much review for everybody, but a quick understanding of the different parts of what we call machine classes. Essentially in Hadoop you have two machine classes. You have a master class and a worker class. The master class is mostly defined as a server that should be high availability. So these can be management nodes, things like the Embari server, the Dame node, the resource manager, obviously the Yarn resource manager. If that goes down, then jobs can't be submitted. Things like the HBase master. These are processes that if they go down, for instance with the name node, if the name node goes down, you're in a state where your cluster is going to be down. So they tend to be single points of failure that require some kind of redundancy or HA deployment. The other ones are worker nodes, which tend to be more fault tolerant of failure. So a data node, for example, is considered a worker node. So you may have hundreds of data nodes in your cluster. Since you're replicating the blocks and you're replicating the data amongst data nodes, if a single data node goes down, it's usually not a big deal. The jobs can recover, the data can be recovered, things of that nature, and mostly it'll be recovered automatically. So worker nodes tend to be you don't need to worry about HA for worker nodes. Now, if we dig deep, your machine classes, your master classes are typically enterprise server class machines with resilient hardware. They're going to have, depending on what they're being used for, they may have quite a bit of RAM. They may have fairly dense cores. So they also tend to be under fairly strict SLA. So if you're going bare metal, it's these master class servers within a Hadoop structure that you really want to focus on making them redundant and powerful enough to handle the workloads. The workers, though, are designed for affordability at scale. You want to be able to buy a lot of them. That's not to say, I mean, they are commodity, but usually standard reference architecture nowadays, even the worker nodes are fairly beefy. I've seen worker nodes as high as 256 gigs of RAM as well as 20 core. So they can be pretty dense. We can talk about that in a bit as we get into virtual environments. So SLAs tend to be non-existent sometimes. the story I tell is in Yahoo they have 40 some thousand nodes, and so what they'll do is they'll just every month they'll just back up a truck and just replace all the servers that went down for that month. So there isn't really any need to immediate replace servers as they fail for worker nodes. This is typical hardware. So these aren't small boxes. So we're looking at a lot of RAM for these boxes. So as always with anything, RAM is good. Hadoop is no exception. Some services like RAM more than others. Obviously, if you're running a Spark engine, you'll want more RAM. Other services tend to be more CPU bound, but I usually see fairly powerful systems. With worker servers, you can tend to, since you're using JBODs, you can beef them up a little bit better. So traditionally, you'd rather see for typical hardware for Hadoop, especially for a worker node, you typically want to see less dense disks. So you would prefer to have 12 1 terabyte disks than 6 2 terabyte disks, for instance. So and there's also cluster and worker types. So there's storage orientated. Again, these are just how dense you want your disks to be. They're storage orientated, which 8 terabyte class drives, where if you're just going to cold archive onto Hadoop, just get the largest disks you can and just fill them up. We mostly see the balanced type. 80% clusters are balanced, so that's traditionally what we see as far as enterprise class servers. And then obviously there's other ways. There's performance and high performance using SSDs, and as well as standard terabyte drives. So again, this is all looking at Hadoop from the bare metal standard. So if you're going the bare metal route, this is kind of the world you're going to live in, and you're gonna look at this type of architecture. But as a what I found is that as you virtualize your Hadoop structure, whether you're coming from a Hadoop admin that wants to virtualize Hadoop or is being asked to virtualize Hadoop by your infrastructure team, or if you're part of the infrastructure team who owns virtualization for your company and you have a Hadoop cluster that you need to virtualize, in any case, if you're the Hadoop admin, you're going to need to learn a little bit about virtualization and understanding virtualization, the components of virtualization, as you virtualize your Hadoop cluster. From the infrastructure side, you need to know how Hadoop processes data, and how Hadoop is different than your standard data processing software in order, again, to virtualize correctly. So either way, you're going to have to look at the other side of the wall and think about what's going on in that environment. You need to know a little bit of both, and I think that works for any kind of. When I was virtualizing databases, it was important to understand to have access to vSphere, have access to the monitoring capabilities, and understand it in order to troubleshoot performance and really create a best of class environment. So let's look at some best practices around virtualizing Hadoop and essentially why you would virtualize Hadoop. So the reason to virtualize Hadoop isn't much different than why you would virtualize anything else, right? If you think about virtualization, the main thing is provisioning. So we have many companies that can take upwards of a month to provision hardware, right? Virtualization, on the other hand, you can spin up a virtual server in a day. So there's the provisioning aspect. There's the resource utilization aspect. The virtual environment tends to, obviously your CTO would much rather see a server using 80% of its CPU constantly than seeing spikes in CPU usage or idle CPU usage, right? So it's a better use of utilization of available resources in your environment. But let's also think of other virtualization scenarios. So cloud deployments is also, considered a virtual option, and we see cloud deployments very popular and getting even more popular. As a matter of fact, I believe HD Insight in Azure is the largest, is basically the largest, how do you say, processing consumption of Azure processing today. So, and HD Insight, of course, is Hadoop as a service in Azure. So we see a lot of companies using the cloud to quickly spin up clusters. They use them for dev and test environments. A lot of, there's some big, very large companies out there that are using HD Insight in Azure for production Hadoop clusters. And again, the cloud has some of the same benefits as virtualization. One of the differences, though, with the cloud is that the only storage that's cheaper than bare metal Hadoop is the cloud storage. So, so something to think about that. Cost is definitely a factor. Easier management. Again, you may have this need to own the base but rent the spike. So we may look at hybrid clusters in the sense that you can account for bursting scenarios into the cloud, seasonal activity, things of that nature. And then we'll talk a little bit about SAN and NAS, and I have some pretty strong opinions about that based off actual user experiences. So if we look at storage, the traditional, we'll just say it right off, the traditional storage pattern for virtualization is SAN. So the majority of your implementations for virtualization will use a SAN architecture. This is actually from VMware, based off Project Serengeti, which we'll talk to in a little bit. But the one thing, if you get anything out of this presentation, is that when you virtualize Hadoop, do not use SAN storage for your data node storage. It will not work. And if you think about the way Hadoop processes data for data locality, it brings the processing to the individual node, and if you think about the network traffic that Hadoop incurs, you begin to understand why the SAN will not work. Hadoop was created for a shared nothing architecture. It does not work well when you're sharing disk I/O with other non-Hadoop workloads. So please keep that in mind. When you're looking at virtualizing Hadoop, you will be looking at DAS storage for your VMDKs, for your data nodes. Now your OS images and things like that can reside on the SAN, but for your data nodes, you're going to want to use direct attached storage. We have had customers, very large customers, that tried it with SAN and it just doesn't work. So I'm going to save you some headaches right now. Keep that in mind. And really, if you look at overall storage costs, again, this is from VMware, your SAN storage is going to, for half a petabyte, it's going to cost you $1 million. If you look at local storage, $1 million would get you 10 petabytes and twice the number of IOPS. So it's not just, there's a cost factor to it. There's also a cost and significant performance factor for using local storage. So save yourself some trouble and use local storage for your Hadoop nodes. Now, with that being said, if we look at the if we look at how Hadoop processes data, VMware, and I'm choosing VMware because it's the most popular virtualization tool on the market. VMware has done a very good job at engineering, creating an engineering relationship between themselves and the Hadoop vendors. And what that means is that they understood early on in an open source project called Project Serengeti that Hadoop had very specific processing requirements. If we think about topology awareness, balancers, rebalancers. So think about it. If you look at Hadoop and you have thousands of nodes, each node has terabytes of block data on it. If you lose a node, that replication factor has to maintain at 3, and so Hadoop will realize that a node's down. Some blocks only have 2 replicas. So it will have to re-replicate all that data, and that's basically a balancer. Or if you add a node to a cluster, initially that node's not going to have any data on it, so there'll be some, you can get cluster skew in your, data skew in your cluster that needs to be, and so there's the balancer that would balance out that data. There's also the idea of reads. When you read data out of Hadoop, and with the name node tracks where every block is located, and so it will tell the client to read the replica that is closest to the client. It's not going to want to go off rack for that read, because that would incur a network charge for that read. So it will do the closest replica. And then there's some task scheduling policy extensions, which are kind of an offshoot from the old map reduce days, but are important when you're scheduling tasks and allocating containers. So essentially what happens, these are all built-in functionalities within the Hadoop software, and what HVE, or Hadoop Virtual Extensions, does is it's a plug-in to your virtual environment that makes the hosts that are running Hadoop aware that it's in a virtual environment. So it's a communication level between the Hadoop processes and the ESXi abstraction layer, which controls the disks and the resources underneath. So it makes each host aware of topology settings, aware of the data, where the data is located within the virtual environment on each host.
Scott, you there? Ladies and gentlemen, he did say he sometimes loses Wi-Fi network, so let me see if I can text him right quick and pick him back up. 1 second here. We'll see if we can get him back on the horn and let him know. Okay, ladies and gentlemen, I do have him on the phone. He's going to log back in, so give us 1 moment and we'll pick back up where he left off there for you. 1 moment. Okay, he's working on, still coming in, so just a moment, folks. He's now coming in, so let me get the screen back over to him. Okay, I can hear you now. Say something, Scott. I can hear you, I believe.
Hello?
Yep, I can hear you.
Can you hear me?
Yep, I can hear you. And I'm sending the screen back over to you, so go ahead and broadcast there. Yep, I can see your Outlook.
There we go. All right. Let me, I'm sorry. I think I lost my name node there. All right. Do you see the screen?
I do, and you're on virtualization versus containerization.
Right. Let me go back real quick because I was going through some best practices. So I think we pretty much got some of the virtual extensions
you were right there.
Down, which, again, just in summary, it makes some of the native Hadoop processing transparent to the virtual environment. So you get things like data locality, topology awareness, things of that nature, executing against the virtual environment. So it's the best of both worlds. And in fact, what VMware has done is they've actually taken the open source Hadoop, they've added code to it, they basically essentially patched it, and then put those patches and that code back in the open source. So now it's part of the native open source code in Apache. So very, very, very good stuff. So basically, best practice, create images based off server functions. So we talked about those master worker type functions. They could be also H-based servers, Cumulo servers, whatever, Spark servers, Storm servers. Create your images based off those server functions. And again, remember base HA requirements, and we're talking about virtual HA requirements off of those server functions. Obviously your master servers are going to want to be HA. So make sure you make those high available in your virtual environment. Always run Hadoop in its own network. Hadoop is very chatty. It pretty much requires a 10 gig network. Also leverage native Hadoop HA, and then leverage virtualization HA for any other services. So, for example, you could try to leverage, virtualization HA for the name node, but probably what is better is just go through Mbari and set up HA for your name node through Mbari, and make sure that your standby name node is on a separate VM host than what the primary is. Make sure replicated environments, your RDBS metastores, like your Hive metastores, your Oozie metastores, your Mbari metastores, reside on different ESXi hosts. Traditionally, what tends to happen is a lot of companies will use existing Oracle installations for their metastores because it's already being backed up and under strict enterprise guidelines and SLAs. Again, use DAS for worker nodes, and also try not to overcommit Hadoop nodes. I think this is the same with any kind of virtualization. If you're virtualization anything, only overcommit if you absolutely know a lot about virtualization and how to recover when you run out of resources. If you overcommit and containers can't be allocated, you will see job failure. All right, I want to point out a quick thing about. I'm not going to go too deep into this. I want to point out a quick something that's happening in the market right now. That's probably going to help. It's probably going to influence the next 5 or 6 years of virtual environment, and that's the idea of containers, containerizations. So, if we look real quick at the difference between what is today what we consider virtualization and what is considered what is considered container, or think Docker containers. Essentially, this is a good chart that shows you. So virtualization is really meant to run a lot of small apps on very large servers. So you think usually your ESXi hosts tend to be large servers, highly redundant. There's a virtualization layer, and then you may have any number of virtual machines running on that server. And each virtual machine is essentially a complete OS and network stack, essentially, including the application. When you think of containerization, it's a little different. You may have a huge app that is running on a type of virtualization service, but underneath is a cluster of many small computers that are all working together to service resources up to those applications. And what we see with something with Docker is that, in fact, when we think of a Docker container, we aren't looking at the entire software stack in a Docker container. You're only looking at the application libraries and the core functionality. Everything else, if you think about the OS kernel and things like that, all that is shared between different Docker containers. So Docker containers tend to be extremely lightweight, and they have everything within them, contained in them, to run the application from a software library viewpoint. It doesn't contain. It's essentially is platform agnostic as far as what kernel it runs on. With that being said, you have to have a way to manage all those virtual containers, much like the ESXi host manages VM servers. So in this case, it's the clustering technology. There's Slider, Apache Slider, Swarm, Kubernetes. It's not clear which one of these is probably Kubernetes, and Docker Swarm are pretty popular. Apache Slider is in development. Currently, it's being used in open source for long-running applications like Storm and things, and HBase and things that want to interface with interact with Yarn. So underneath essentially the Docker management software is Yarn, which is the resource negotiator for all those containers. Another resource negotiator that's associated with Docker is also Mesos, which is also used in many companies. So, and then at the bottom you have your HDFS storage layer. So this is a shared storage layer. It is the data platform that essentially contains all the data you need to serve up to your applications. So it's essentially a cluster of computers that store the data, and that so it really is this concept of a data lake, and then tied into that are things like management, cluster management, security, and data governance. So the idea is that we may be moving a little bit. See, even in the world of Docker, we start to see VMs become somewhat heavy in use, and then again, they don't tend to, they're not, they don't tend to be able to access this same a centralized enterprise data store, which is provided by HDFS. So so we're going to start seeing here in the next year or so a development from moving into this approach of Docker. So even your data nodes and your services within Hadoop could actually be presented as Docker containers, all managed by Yarn. And what that provides you is it provides you ease of use. It's extremely quick to deploy Docker containers. You're going to have scheduling features, isolations, things like um, capacity scheduler so that you can fence off resources to different groups within your organization, and then also lower barriers to adoption and stability. So something you can do with Docker containers. It's very easy to just take a Docker container and move it. If you have a data center in the Midwest, you can move it from there all the way to Europe and see almost no disruption in processing for that container. So extremely interesting technology that has a different spin on your traditional virtualization world. So some key themes is that this is a way to move more towards a data-driven organization in which you don't create these silos of applications like you do in your traditional virtualized environment or even in your bare metal environment where you create an ERP system or you create a CRM system that has its own database. Instead, you are essentially ingesting the data into a single data platform, then serving that up into whatever applications you have. But you're letting the data drive the application. And for Docker, applications become truly agile. You can build them quickly, you can change them quickly, and deploy them quickly. Central data repository, what we call the data lake. It's also interoperable with existing systems, ease of use, and the maintenance and scheduling is essentially baked into the platform. So if we look at some parting thoughts. From my personal experience, there are some benefits. One of the benefits to virtualization is that you get the ability to run older systems on newer virtual hardware because it's abstracted away. So that can be valuable if you want to start changing some of the underlying hardware separately than upgrading your software. Be able to isolate, again, what are Hadoop issues and what are virtualization issues. That's where it takes really your team working together, your Hadoop team as well as your virtualization team to work together to diagnose the whole stack within a cluster. And we actually see some companies looking at ingesting their vSphere logs, their monitoring logs, into Hadoop for analytics, for capacity planning and things of that nature. So there really can be a good coordination between the two platforms. Keep in mind too to server sprawl. So I'll tell you, if you guys want to, we sell support by the node. So if you want to sprawl, go ahead sprawl. But I'm going to warn you that in any virtual environment, there is the tendency to because of the deployment provisioning is so much easier in a virtual environment, there is the tendency to just start throwing servers at the problem. And another challenge with virtualizing Hadoop is as compared to bare metal, is that the servers themselves tend to be much smaller. So you probably will have a number of, you will probably have in total more nodes within your virtual cluster than you would in a traditional bare metal cluster. And then always use the latest and greatest version of VMware as well as the latest and greatest version of the Hadoop virtual environment plugins. So make sure you keep up with the developments in those areas. So for some final thoughts, we really need to start thinking of not individual servers, but of the cluster, and that goes whether you're doing bare metal Hadoop or virtualization Hadoop, virtualized Hadoop. We are thinking, in a Hadoop environment, you're not thinking individual servers. You must think the cluster and if you're used to virtualization, this shouldn't come as a surprise because even virtual environments are cluster based. But it is that the environment, it really is a bunch of servers that are presenting a aggregation of all their resources for compute. So it's a different way of troubleshooting. It's a different way of approaching the architecture of the platform. Again, Hadoop essentially is not that much different than virtualization. The cluster is a pool of resources, but it's also a pool of data, and I think that's where the difference is. You have cluster resources, but you also have cluster data that most tools out there today can access and interoperate with. Again, you need resources to access the data in the cluster. The resources and data are the same. Data is a resource in your cluster. What we like to think about is today we talk about a database administrator or a database application developer. I think as we move forward into more cluster-oriented thinking and data-driven thinking, we need to start thinking about a data administrator or a data application developer. So the database in this world is just another application that uses data in order to present it to the end user. But that source of that data is really where the cluster resides. So some further reading. VMware does have a book out called Virtualizing Hadoop. I drew a lot of this presentation from points in that book, so I strongly recommend it. Romel Garcia is actually an SE for Hortonworks, and so we work closely with VMware to give a best practice and overview of how to deploy Hadoop and optimize Hadoop in a virtual environment. There's also a really interesting book that Google produced, that Google wrote quite a few years ago called Data Center as a Computer, and I think it was the beginnings of both cloud architecture as well as things like Docker architecture, where the data center just becomes a collection of resources that works together to serve up processing to applications. So really interesting read. And then I have a list of resources. And with that being said, I'll be happy to take any questions. And any questions I can't answer here, I'll make sure to jot them down and give them back to Tom, who can disseminate them to everyone.
Well, again, Scott, thank you for your presentation. That was very informative. We can get any questions. There were no questions at this point. And if you guys have any questions, please post them this time. We want to again thank Cisco for being our sponsor this month. Terry Phelps, I will send you an email after a while, and you are our winner of the $100 gift card today. So we appreciate that. Someone asked, can you go back to slide 1, please?
Go to slide 1.
Go to slide 1.
All right.
See what kind of questions they might have.
All right, here's slide 1. This is slide 2.
We wanted just a reverse one from the end. From the very end.
This one?
Go to the very end. Looks like you said reverse one, not go. Go to your very end of it, Scott.
Very end? Oh.
Go to the very end and go back one.
Oh, yep. The books?
Yeah, there you go.
Ah, yeah.
Okay, second slide to last. Okay. Yep, that's what he was looking for.
Okay,
I think he was looking for the book names and stuff. So.
Yeah. Great.
All righty, no other questions here. So if we have no other questions, again, thanks. Great presentation. I will get this posted online. Sorry about the video, audio going out for a minute there. Yep. I think we recovered quite well there. And someone said they totally loved it. So you did a good job.
Oh, wow. Thank you.
All right. Thanks again, Scott, and we'll have you again in the future when you tell us a little bit more of why we should or shouldn't virtualize Hadoop and how it's changing, because I know it is constantly changing today. So
Yes, it is. All right. Well, thanks, Tom. Thanks, everyone.
thank you.
Bye.
Goodbye, everybody.